session on data science. If there are any queries from the previous session, we may get started with them before people join. We are only, I think, 30 people now. So possibly if required, we can just quickly address some of the queries that you have. If you remember in the last class, we started understanding about the handling of outliers, handling of missing values. Of course, I did not cover all the mechanisms. I said possibly when we deal with some other, when we talk about unsupervised learning, clustering kind of problems, we would be solving some of the missing value identification, missing value imputation kind of mechanism. Then we could also look at outliers. We have multivariate outliers, which can again be handled through clustering kind of algorithms, or even the typical ensemble based model algorithms as well. Similarly, for skewness and kurtosis also, we just talked about possibly trying to make the data normal by trying to do some kind of non-linear transformations on the top of the data. So those were some of the things. Obviously, when we do a one end-to-end project or a few end-to-end projects, it becomes more easier for us, or we can relate to all these things. So once I complete all the concepts with some data, then we can also move ahead. So we have talked about all these things. Skewness, how do we handle it? Right? In some cases, we handle it through the square roots, we can handle it through logarithm, and depends on whether your skewness is positive or negative. We talked about those aspects as such. But of course, as I told you, there is a slightly more, what you call a more generalized form, which is otherwise called as a Box-Cox transformation or a Yo-Johnson transformation. So this is something which is a generalized form of, you will get a logarithm, you will get square root, you will get square, you will get reciprocal, all these transforms as a special case of these two transforms. So I'll try to apply these transforms in the next examples, or possibly when we deal with the real world case studies. But right now I'm moving forward in terms of the other aspects as such. But yeah, in the meanwhile, if anyone is having any clear. So what was that last topic that we are talking of, skewness? So from where do you want me to talk about? So this is possibly we are talking about handling skewed data. Okay, so if we really see here, see most of the times what happens is we end up fitting some kind of model to the data. So possibly the first choice would always be some kind of linear models. So it could be a linear regression, it could be a logistic regression. So these are all some kind of linear model. Now, linear models definitely assume that the relationship between X and Y is a linear relationship. And they also assume normality among the individual observation. So multivariate normality is nothing but each individual variable is normal in itself, and jointly also they follow a normal distribution among them. Bivariate, multivariate, normal distribution among them. So in case our individual data is not normally distributed, then the first option is I cannot apply linear models on the top of that data. So what are the alternatives? So which means data not normal, all kinds of linear models, they are knocked off. All kinds of linear models, though you may fit them, they will not emerge out as the best possible model. So what is the alternative? Either use non-linear models or do some kind of transformation of non-normal data so that it can improve towards normality. It can move towards normality. So it may not be perfectly normal, but it might be coming more closer towards normality so that you can apply linear models on the top of it. Because our data has come more closer to normal compared to the original data, I can think of applying linear models to that data. So that is the fundamental. So that is what we meant by handling the skewness in the data, right? So what is that we are saying through the example? You can very well use some kind of mathematical functions on the top of that data, either to reduce the range of the data or to increase the range of the data, depending on whether the skewness of the data is positive or negative. If the skewness of the data is positive, then we would think of reducing the range. So some kind of transformations which can reduce the values like square root, logarithm. These all actually reduce the value, cube root, reduce the value of the observation so that the range also will get reduced. And because of that, something that was very kind of extreme value, which is increasing the skewness, would now come into the range. Whereas if your skewness is negative, I want something that would expand the range. So possibly doing e to the power x or doing a square or a cube kind of a transformation can typically increase the range, which means possibly they might increase the skewness and try to take it closer to zero. But whatever we do, we already know what is the kind of transformation that we are doing on the data. Because of that, it's not a kind of a manipulation or anything. It's a kind of internal workout so that I can try to make my data more closer to being normally distributed. Now, these are the specific functions, but that's where we talk about two major broad functions called power transform. Possibly, I'll use them in another example, right? Probably once I finish off some concepts, I want to actually run two case studies so that you get a lot more comfort if I have to solve an end-to-end problem. So we use a Box-Cox transformation or we use an Eo-Johnson transform. Once we come towards the model fittings, I'll run one case study where we compare across multiple models and something like that. So Eo-Johnson transform, so I'll put the power transform there. So these are where I mean, basically you will be seeing later that all these square root, logarithm, cube root, e power, all these will come out as special cases of those Box-Cox and Eo-Johnson transformation. Does that answer your question? Now things are okay, or you have a follow-up question? Dave, I think you had this question. So that is where I was talking about initially checking for the skewness. Look out by using the QQ plot, how much the data is adhering to normality or deviating from normality. I see that the skewness is positive. And if the skewness is positive, then look at for those transformations which can reduce the skewness. So log transformation, if we are putting, the skewness will be reduced because the range will be reduced. So possibly I'm applying a log transformation on the top of the data. I could see that the QQ plot is more or less fitting to that red line. And even I could see that the skewness has come almost closer to 0. So rather than working any kind of a future workout, rather than working on the living area, I would work on the logarithm of the living area because this data is more closer to normal, and hence I can very well apply some kind of linear models. Similarly, we are seeing instead of logarithm, can I look at a kind of a square root transform? So like that, we are trying to apply different kinds of transform, but the square root has given almost 0.339, but looks like the other one, minus 0.12 is very close to 0. Other variable could be a one-digit number. Still have to address for the skewness. If at all, we want to apply a linear regression model to the data. So these are all a part of handling and doing some kind of pre-processing on the data. Now, so as we clearly, as I've already been telling, linear regression assumes that all the data is normally distributed. Univariate normality, bivariate normality, multivariate normality. Most of the time, what we do is we end up directly applying linear regression on any data that is given to us. But most of the time, we fail to check for all these kinds of linearity related assumption. Right? Now, one more important point that we are talking of course, sometimes this may not make much sense in the linear regression case, right? Now, the next thing that we talk about before building any kind of a model is doing some kind of the standardization of the data. What is standardization? You try to bring all the data items, all the features to a common base. Now, what do I mean by this word, to a common base? See, sometimes we have one column called age. We have one column called salary. So age might be a 2-digit number, but salary might be a 6-digit number. Right? And on the other hand, some other variable could be a 1-digit number. So this is one or impute the missing value. So at this step, you will not be having any missing values as such. I hope I'm clear on that. So yeah, that is one. Put the mean. I also told you that there is a risk with putting the mean median. I hope you have gone through that. But often forget while working on new data. It's very. So that's where we will do a end-to-end case study also. Right there, I would like to see that we don't get into all of so these things. You have to. I mean, possibly it's always better to put a kind of a sequence. So in a case study that I'm going to discuss, at least I have put all in a form of, because once you know all these concepts, then I can, when I'm explaining the concepts, they would not be in one single order. That's the reason each concept is coming in a different location. But typically when we do a case study, by that time we are very clear on all the concepts. So it would be very easier to put a kind of a sequencing to the steps that we are planning to do. So there is a Z score, or sometimes you can very well use a kind of a min-max scalar. So wherein you can simply subtract every observation. From that every observation, you subtract the minimum of that column, and you typically divide by the maximum of that column minus the minimum. So basically, the denominator is nothing but it's a range of the column, and the numerator is x minus the minimum. X is your individual observation. This way, what happens is for all the columns, the minimum value will be 0, the maximum value will be 1. So here we are standardizing the minimum and the maximum values of each column. Whereas here we are standardizing the mean and standard deviation of each of the columns. So there are a few other mechanisms also, right? Possibly you talk about maximum absolute scalar. So there are different other such kind of a scaling mechanisms that we can do. But most prominently, we end up doing these kind of standardization, right? Once we standardize the data, after that so this is one mechanism involved in your day-to-day work. Standardization does not change the distribution of the data set. Normalization does not, when you are doing a Z score, it does not change the distribution of the data set. But min-max can change the distribution of the data set, right? Because min-max is mostly a kind of non-parametric mechanism. So it can very well change the distribution of the data set. But there are a lot of algorithms that we would be applying, which are more non-parametric in nature. And because of that, possibly it does not matter much. Paras, if you don't mind, if you can post your questions in the chat box itself, it would be better, because opening two things would be difficult at any point in time, just for a comfortable side. Okay. What is more, see, okay, I have only one single mantra in all this. There is nothing called this is preferable or this is not preferable. Right? The only thing is, here the mechanism is quite interesting. We are building our model on the training data. We will build it, we will test it on the testing data. Right? And we would be looking for accuracy or some metrics on the testing data. Okay, that's what I'm trying to say, Sachin. There is nothing called, nothing called this is the best, right? So in many cases, what can very well happen, that's where what people do is, they build some kind of pipeline, wherein in the first pipeline, I can very well use a kind of a standard scalar, which is doing a Z score. In the other one, I can very well use a min-max scalar and try out different algorithms. But at the end of the day, my rules are very clear. I build the data on the training. I build the model on the training data. I test it on the testing data. I want to see wherever my metrics are, performance metrics are doing better, I would go ahead with that approach. Okay. So going by that, So regression models, you're going with the standardization, zero mean, unit variance. Of course, standardization you cannot perform on the categorical. So categorical, I have one more process which I think in this notebook only we are going to discuss. For all the categorical data, we would be doing something called encoding. Categorical variable encoding. We will be discussing a few types of categorical variable encoding somewhere toward the bottom of this notebook itself. So this one, standardization, right now I'm doing it only for the numerical data. We don't do it for categorical data. So that's the reason initially we would separate the data into numerical and categorical. So that's where I'm looking for if the data types are in integer 64 or float 64. So which means they are integers or float. We can do an info. Once we do an info, we get the data types of all the columns. So depending on those data types, you segregate those data columns with the integer and float data types. Based on that, you call them as numeric data. You separate the numeric data. And whichever are not numeric, so we are subtracting the difference from the numeric features. So we are taking the columns and the total columns minus the numerical column. So they are all the categorical columns, which means I'll simply take that as my categorical data. So I have segregated my numerical data and my categorical data here. What could be the other techniques for standardization? You can very well do many, right? One by that. So these two are actually supported in scikit-learn. This is also supported in scikit-learn. As I told you, the third one is also supported in scikit-learn, where I can divide it. So the max absolute scalar is typically it is doing a kind of, let me just check what exactly it is doing. It divides by the maximum value. Each feature, maximum absolute value of each feature is set to 1. So you are not subtracting anything. You are dividing by the maximum value. So it does not shift or center the data. So basically here, the max absolute scalar is nothing but you are doing x by max of x. Right? So only the maximum value is what you are making it as a kind of a you are for all the columns you are freezing on the maximum value to be 1. Like that, I think there are a few more which are supported by different softwares, whereas in sklearn, scikit-learn, these are the three major things. But sometimes you can also take x divided by the standard deviation of the column. So this is also that's something that is typically taken as a kind of standardization. So there are a few such kind of functions that can very well be used, or you can even design your own function. But I see that the most commonly applicable functions are these. Okay, then I think I missed out. What will we do for categorical missing values? Even that I have discussed. Okay, let me just finish up. For categorical missing values also, I will come out with the mechanism. We will have a mechanism to convert the categorical variables to numerical. But I have discussed a few things. One as a part of imputation. So there are, all those things that we have done for numerical, they are applicable for categorical also. Remove the rows, remove the columns, replace them with a constant, right? Or replace them with some function like a mode. Mode would be more appropriate. Or you can do an imputation, model-based imputation. You can do even for a categorical variable also, right? So all those are very much possible. If you have further question, then you can just ask. Could you please explain the difference between multi-label and multi-class? There is nothing as such, right? Label is the name that you are giving to your target variable, right? Or sometimes normally when you are saying multi-labeled models or multi-labeled multi-class models, they mean one and the same, because the word label is the term that you are using to the target variable. Class is also a kind of a word that you are using to the target variable itself. At least as far as my understanding goes, there is no difference according to what I understand, but yeah, possibly I can look at it and get back. Numeric features. So these are the columns where only numeric data is present. I'm really not sure of the name, Dave. I don't know whether there is any specific name to some of them. I mean, these are the very common names that are available in the package like scikit-learn. But sometimes while doing the adjustments, we can do all these. So I'm really not sure if there are some specific names, because most of the times we end up using one or two of these transforms itself. Okay, then. So we are looking at only the numeric data. So you could see here the subclass, frontage, lot area, overall quality, some of these things which were there as numerical. So we don't know, sometimes it would have been better if we had converted them into categorical, because subclass may not be a numerical one, right? Though the numbers are there here, it might not be a numerical column. It would have been better if it had been converted into a categorical column. But now that we did not do it, we'll just go ahead with it, right? So because when you plan to do it as a kind of a full-fledged case study, it is very much required that the data types which are not appropriate, better convert them like numericals, you convert them into categories, and if there are any categorical, better convert them into numerical. So in case of categorical data, these are all the columns that are there right now. But right now, I am not looking on categorical data, right? I would work with the categorical data slightly later. Here I am only demonstrating each of these things. So that's the reason I have segregated the numerical data and I have segregated the categorical data. Now, yeah, I think our friend has already said if there are missing values, that is going to create a problem. Paras has already said that. So which means by now we would have already done all the necessary handling of the missing data. Either removal of that data or doing some kind of imputations on that data. Right? Possibly if we have not addressed all, I'm simply using a simple strategy right now. All others, impute them with the mean. Whatever are the data that I am right now having, if at all there are, possibly we'll look at first, okay, because I might have already done the imputation and all, right now it will not show any because I'm running the whole code before I'm explaining, because I don't want any kind of a processing delays to happen when we are discussing. That's the reason I'm running the entire code before we are explaining it to you. So by now the whole code would have run. So even if I do a kind of a numeric data info or something to find out the missing values, it will show 0 because it would have imputed them with the median already. Right? So we are going ahead with a simple strategy where I say impute the missing values with the median. Right? And so which means I'm initiating this process, imputation process, and I'm simply transforming my data. So whatever is the numerical column that I have, if I have any kind of missing values in any columns of the numerical data, rather than omitting those columns, I will replace them with the median. I can do it with the mean as well. So in the simple imputer, I can very well replace them with the most traditional kind of function. I can use the mean, I can use the median, I can use the most frequent. Most frequent is basically like a mode, especially if I have categorical columns, I can very well replace them with the most frequent, or I can replace them with a constant. So I can specify the constant and I can replace that with a constant. So either I can give that as a numerical value or even with this. So like that, I can very well specify what is that I'm doing with the blank values, and just retaining those numerical columns. And that's so basically now if I look at the info after doing this imputation, definitely all the columns are showing 1455. All the columns are showing, all the numerical columns, all the numerical columns are showing 1455, which means none of the columns, none of the columns right now, they look like having any kind of missing value. Okay, let me look at this question. Is there anything difference? Okay, fair enough. I'm really not sure on this dimension, but yeah, possibly we can discuss on this. Okay, so once we look at it, so it looks like the data is already imputed. Now, if I look at if any of the columns are blank, I can even check it with this kind of a mechanism. Of course, my info is sufficient. In info, I'm getting all values are all the values are 1455. So I don't see any kind of blank values anywhere. But even this one can very well check if there are any missing values in the data. And these are the columns, right? And we can very well use this scale. So standardized scaler. In we are typically having the standardized scaler in a scaler, right? Possibly I can let me do one thing. So you do this, then initialize the scalar, then fit. So you can do this. So basically our data is nothing but imputed DF. So you can very well fit this as well. So you will find possibly the values are typically fitted. You can save it into a variable and you can very well get the values to be printed, right? So the same thing, you can very well use a pre-processing not scale, and so you can get the data typically the values to be printed. So your data can very well get transformed into a scale in case you are doing a kind of a Z-score computation. So especially if there are data, age, then salary, which are having different dimensions in that are different units, possibly 5-digit numbers, 2-digit numbers, etc. Then basically, if we are using a linear regression models or something, you will always find the difficulty in interpreting the coefficients. So by doing this standard scaling, it's always better in case of parametric models. Always do your standard scaling, because there we are not disturbing the distribution of the data. Whereas in the other forms of scaling, the distribution of the data gets distorted. So especially if you are using non-parametric approaches, there it is pretty much fine. But when you are using a parametric kind of approaches, it's better that we use a Z transform or otherwise a standardized scaling, right? So then the alternative. So scaling, standardized scaling is what we call it as a Z-score. Then here, as per the scikit-learn terminology, there are other things like min-max kind of a scalar, which we have already discussed, or absolute max kind of a scalar. So it does not matter. So you can very well apply, right? You can use a fit transform rather than a fit. Possibly in this case also, instead of a fit, you can also do a kind of a fit transform to directly print out the values. So you'll get the values printed. So you can very well apply different kinds of, so you can import a standard scalar, or you can go with a min-max scalar, or you can go with max absolute kind of a scalar. So there are three different scalars that are available. And in each of the cases, you can very well apply that particular scalar. And you have also looking at the columns, whichever you want to transform. So we have already got a list of the columns that we want to transform, which are all the numerical columns. So for all the numerical columns, you can very well go ahead with doing this kind of a standard scalar. And the same way you can try out with the min-max scalar. You can also try out with the max absolute scale. Okay. Now, we have also talked about the normality of the data, right? So after you have done the scaling, if you have done min-max scaling, the distribution of the data would not have got distorted. But if you have done any other scaling, because if you see here, I can very well plot a normal distribution to the data. Scale is nothing but you are doing a scaling, x minus mu by sigma. Okay. So that is what we are doing as a part of a scale function. It's a standard scale. So we are putting a normal distribution to the data. And what we could typically see, the blue one is the histogram. The blue line is what is the density function of the data. And the third one, the black line, is what is the normal distribution line. We have fitted and we are doing a kind of a probability plot. Probability plot is what is typically giving me that this is a kind of a normal distribution. So obviously we see that our data is slightly deviating from the normal distribution itself, which we have clearly seen here. But this kind of a quintile plot is a very good indication for us. You could see here the theoretical quantiles are coming down, changing, but the ordered value, which is your empirical quantiles, it is showing a 0 only, right? Probably until some percentile. So which means there is a lot of concentration of zeros in the data. There is a lot of concentration of zeros in the data. So which means a logarithm transformation would not have done a job here. Logarithm transformation would not have done a good job here. Or even if I apply a logarithmic transformation, then I may have to apply only for non-zero kind of values, because logarithm is not defined for 0. But in our data, I'm seeing a lot of zeros. So which means better I use a square root transform if at all I have to address this non-normality kind of data, or I use the logarithmic transformation only on this positive, only on the positive values as well. So like that, we may have to think through, right? You can apply a square root transformation. So once you apply a square root transformation, possibly you could see here the actual histogram. The blue one is also talking about the density function, and to a large extent the normal distribution plot. They are coming pretty much closer compared to the earlier case, and you could also see that the QQ plot is looking like more or less on the red line, indicating that there is a decent normality in the data. The moment I ended up fitting a but here, if you see, I have fitted a square root transform only for that particular data. If you see here, okay, here we have segregated the data, right? So we have used one additional parameter, or one additional variable called new basement, where we have said if the total basement value is greater than 0, if it is 0, I am not considering it. If it is greater than 0, I am setting it equal to 1. So like that, I have almost 1418 houses where the basement value is at least greater than 1. So which means out of 1455, I think some 27 of them, they are typically having a kind of 0 with the basement square feet. So what is that I'm saying? I'm only including those rows. So all those that had zeros, I'm simply excluding them from my data. And once I exclude them and then do this normal distribution fitting, it looks like I'm getting a much better result. I'm getting a much better result closer to normality. So which means what could very well happen is, if at all I want to utilize this variable, so I may find that 0 in the total basement kind of a variable could be a kind of wrong data entry, and because of that I may want to delete that particular entry as well. So in those cases, you are removing the outliers altogether. Because if you keep all those zeros at any point in time, on that zeros, you will always get that horizontal line. And because of that, they may not be very much in line with the normality in the data. So we may want to handle all the zeros. Wherever the basement is zero, I may want to handle it separately from the ones where the value is not zero. So I may want to build two different models, one for zeros and one for non-zeros. So those kind of things are also pretty much possible. That is one more, right? Can it be converted into a categorical variable? I can very well convert it into a categorical variable. I can say zeros and non-zeros. Or you put a couple of other groups as well. 0, possibly saying between 0 to 10, between 1 to 10, about 10. You can very well create, but again, it all depends on how much of aggregation you are trying to do. But yes, that is also a kind of a solution. Nothing wrong in that. Okay. So it's just I have given a name. I don't think it's anything. Normally, when we are building a model, when we are using the residuals, we generally use that res. But here I have just used as a kind of a variable name, nothing more than that. Then, okay, so I think whatever we have done till now, whether it is in terms of creating a new feature or when you are updating an existing features, or when you are deleting some of the existing features, you are changing some kind of rules associated with some features. All these things come under the overall umbrella of feature engineering. But primarily, you can also think of creating. So we have looked at modifying the data, modifying the features, right? Doing some kind of transformations on the features. We have also we would also be looking at deleting some of the features, possibly in the next notebook, right? Which is called as feature selection. So all these things. Now here, let's say I want to create some new features. All these come under the broader heading of feature engineering. You do a lot of, you are manipulating with the features. But of course, that is something that you do based on the domain knowledge. So you create some new features, possibly divide two existing features, add two existing features. So you may require a lot of domain knowledge for that, right? So you may want to sit with a domain expert, and based on his or her suggestion, you may want to either do some kind of arithmetic manipulations on the existing data, or you may want to create some new data by doing doing some kind of manipulations on the existing data, right? So feature engineering is one more differentiator when you are building a machine learning model, because you are bringing in some new columns into the data, which let's say I'm having different values relating to the data. Let's say I'll take a simple example. I have the interest rate related data. I have the stock price related data. I have, let's say the volatility of the stock. Let's say all these values are available. And I integrate all of them based on some kind of domain knowledge. And I simply say, what is the option premium as per some Black-Scholes model. So I compute some kind of a premium by using the option value by using a traditional Black-Scholes option value calculator. Rather than using all these variables separately, I integrate all of them. Let's say a very simple example. I have revenues of the company, I have expenses of the company as two different variables. I simply say, rather than using revenues and expenses separately in my model, why not I compute something called profit, and which is nothing but it's a simple subtraction between the revenues and the expenses. And I use profit as one of the variables in my model. Now, those kind of things are very much possible. That's also something a part of creating new features, which is also a subset of feature engineering. So coming up with the features is quite difficult. New features, time consuming, and it also requires a lot of expert knowledge. So you are relying a lot on experience, domain expertise, and whatever is the kind of empirical comfort that you have working with the data. So you can very well do a new feature creation using domain expertise. You can think of combining some existing features. Sometimes your input may consist of 4 different columns A, B, C, D. But let's say we talk about administrative expenses, selling expenses, marketing expenses. Let's say we have collected all these 3-4 traveling expenses. So we have collected 4 columns of different expenses. So it may not look like, if I'm considering all 4 different variables, possibly I'm not getting some kind of broader picture about that data. So in that case, I may very well prefer combining all the 4 columns and say total expenses. So those are also basically based on domain knowledge. You can come out with that kind of a mechanism, combining a few features into one single feature. There could also be a mechanism of encoding of the categorical variable. We have not handled the categorical variables till now. So if at all a kind of categorical variable is present in the data, what are the various ways to handle it? And in some cases, especially when we work with time series data, which we are going to handle slightly later, possibly the features that are associated with the time series data are something like the trend that is present in the data, the seasonality that is associated with the data. So these are some of the features that I can directly extract from a time series data, especially the trend, the seasonality, etc. When I discuss about time series, I'll come there. Similarly, in the natural language processing, also we talk about coming up with some new features or extracting some existing features from the data. So when we talk about the text mining and all, we are going to discuss about this. So these are some of the things I think we have already talked about them. So basically here, if I want to do some computation like pool score, which is nothing but pool area multiplied by pool quality, or someone wants to do total bathrooms is equal to full bathrooms plus half bathrooms. So all this. Basement full bathrooms, basement half bathrooms. So these are the various columns that are there in the data. Rather than having all this kind of information, why don't I simply combine them into total bathroom? So sometimes I may want to reduce some of the features by introducing something like this. Okay. So possibly depending on whatever are the typical cases that we are going to look at, some of these options would very much be possible. Now I am moving on to the next topic, which is what if there are categorical variables in our data? Right? Categorical variables are all possibly the text-based kind of variables. So till now we have been focusing only on the numerical, but we will be encountering a lot of string-related variables. And if you try to really think, NumPy is one of the most heavily used, right? And we have been using a lot of other functions from various libraries which use NumPy somewhere or the other internally. And one thing that we would have noticed is NumPy works purely with the numerical data only. So if at all I am giving some kind of categorical columns as an input to some NumPy function, I will get errors. So which means somewhere or the other, I have to make my data more or less in line with numerical. Something that looks like a number. Though I am having a categorical data, I should be in a position to convert that categorical data into a numerical data. That's it. And that is the process of encoding. Wherever there is a categorical data, I want to convert it into a numerical data, and that process is typically called encoding. We have different kinds of encoding, right? And of course, in different scenarios, we would be using different forms of encoding, right? So we will look at that. So we could, as we have already discussed, if there are any column which has kind of strings or categories, right? There is a slight difference according to me, string versus a category. String is something which could be any text. Possibly I may not be utilizing that text for doing any form of analysis. It would be a simple identifier or some such kind of a text. That text will not carry any kind of a groupings or any information per se. Whereas when we are talking about a categorical variable, there is a lot of information that is typically being carried. We may want to use that variable as a part of our modeling process, right? So there is a lot of importance to that particular variable, which is typically treated as a categorical variable. So we have different such kind of categorical variables. So one way we may say most of the algorithms, they work only with the numerical data. So which means my data contains categorical data. So which means drop those columns, only work with the remaining data. But that is where possibly there are a lot of columns where very, very important information is lying, and I may be really losing out on that information. So removing the categorical columns is a very bad idea. So which means I have to have a mechanism which will convert the categorical columns into numerical columns. Now, out of the various encoding, now let us see in sklearn, scikit-learn, what are the various encoding mechanisms that are there. So these are all the various functions that are supported in pre-processing, right? So we have right now looked at the min-max scalar, max absolute scalar, right? And probably a standard scalar. These are some of the scaling. So it looks like there are some robust scalar also. Let us see what this, I think our friend Paras was asking. What are the other scalings that are possible? So there is one. This scalar removes the median and scales the data according to the interquartile range. So this is also one more thing. So possibly it looks like, what is that? This is called robust scalar, especially if your data is too much deviating from normality, etc. You can try out doing this. You are subtracting the median of the data and you are dividing it by the interquartile range of the data. So this is one more kind of a scalar that is coming out, right? So you can very well see whatever are being supported. There is a robust scalar, min-max, max absolute. So these are some of the scalars that I am seeing, right? Okay, so these are the scalars that I am looking at. Then the next thing that we are looking at right now is encoding. So this is a label encoding. Right now we are looking at label encoding. I would also be looking at ordinal encoding, and it would also be like a one hot encoding. So these are the different kinds of encodings that we are seeing, right? So encoding is about converting a categorical variable into a numerical, kind of making it equivalent. Can it instead be converted to a categorical variable? Okay, I think I have already seen this point, right? Okay. So, okay, label encoding, encode target labels with value between 0 and n classes minus 1. So all the labels, they are given values between 0 to n minus 1. So you could clearly see that if I am having some such kind of values, right, 1 would be given a position of 0, 2 would be getting a value of 1, and 6 would be getting a value of 2, because it starts with 0, 1, 2 kind of values. So any categorical or numerical value, sometimes what people say is, if I can give a kind of a ranking to the observations, that is also a kind of a label encoding. I give a kind of a ranking to each of these observations. If there are too much of outliers and all present in the data, I might very well simply do a kind of a ranking to the observation, which is also a kind of label encoding from my side. Or if you now see this, if you now see this, Paris, Tokyo, Amsterdam. So obviously, you could clearly see Amsterdam will have a value 0, Paris will have a value 1, and Tokyo will have a value 2. When you are doing this label encoding, so you can very well have such a kind of alphabetical order wise the encoding of the values being done. So this is more appropriate. When is this kind of thing more appropriate? When there is a natural sequencing of the observation. So some kind of ordinal data, if it is present, then you can very well think of doing a label encoding or even an ordinal encoding. Both of them, they have a lot of similarity. This is only when there is a text, but yeah, you have to be very clear, right? In a label encoding, we are just giving some in the ascending order of the values or something. We are giving some kind of aliases, numbering, numerical aliases to each of the column. Okay, let me come back. So let's say here we are talking about for each of the columns, this code is telling me to apply. So you see, all the columns that I want to encode, I am looking for all the categorical columns. All the categorical columns, I am saying that I'll do an encoding. I'll use a label encoder. I'm initiating a label encoder. And whichever are the columns that are there, I'm taking that column and I'm doing a fit transform for that particular column. Label encoder is what I'm fitting the transform, which means that particular value would be printed. Now you could see here, for each of the columns, such a kind of label encoder has been created. But if your data is not having, if that column does not have natural sequencing, then the label encoding will be a big problem. If your column is a nominal column, like for example, we are talking about a column called marital status. A column called marital status. So you will say single, married, widowed, divorced, something. Okay. So if I do a kind of label encoding here, possibly divorced will get a code of 0. This will get a code of 1, this will get a code of 2, this will get a code of 3. Now, because now internally it became a number, it somehow says because 1 is greater than 0, then we somewhere are making a kind of an assumption that M is greater than D, married or greater than divorced. So there is no meaning sometimes, right? Similarly, because 2 is also, so basically you say 3 is greater than 2 is greater than 1 is greater than 0. So you may simply say the widowed is greater than single is greater than this great. So there is no meaning to this kind of a discussion, right? So in this case, and also sometimes probably if so I cannot typically use it in a model, because in a model what will happen is each of these things would typically they have got converted into numbers. So any model would typically treat this as a numerical data, and it will give the relationship thinking it as a numerical data. So all our results are going to get very well biased if we do not handle this situation. So one thing we have to be very careful with is label encoding is always a troublesome thing, especially if your data is nominal. If your data is ordinal, once again, if your data is ordinal, it is very much fine doing a label encoding, right? As I have told, let's say you have, or even if it is a numerical data, also label encoding is good. Probably if you are having a data something like this, as we have shown earlier, right? Sometimes I may say that this is a very highly skewed kind of a data, right? And probably I don't want to use it as a numerical data. I think one of our, earlier we have seen probably if at all there is a very heavy skew that is present in the data, then I can try to address that skewness by doing this also, right? Probably I am converting all of them in by using a label encoding. So this would be one value, these two will be the next value, this would be the next one. So because of that, I can very well reduce on the skew of the data by doing this kind of a label encoding as well. So possibly if I am talking about, so wherever there is a kind of order in the values, and they are also represented in the same order, right? In that case, and there is a meaning to the greater than or the less than associated with it, then you can very well go ahead with the label encoder. I hope you're able to get the point. In case of any unknown data set, how to identify label? Should be taken help from the expert or any manual? Yeah. So label, so basically we would be doing a kind of descriptive statistics at the beginning itself, right? And yeah, see, many a time if the labels are more okay, if the label is more ordinal or nominal, sometimes if a domain knowledge is required for that, I think we should definitely take the help of domain expert. But initially you would be doing a data description, descriptive statistics. So you would be knowing how many categories are there in each of the column. Now, what is the kind of relationship that is existing between each of the categories? Are they related by a greater than or a less than kind of a relationship? Then it becomes ordinal. Then in that case, it would be better to do either a label encoding or an ordinal encoding. Whereas if we say no, they are all they don't have any relationship greater than or less than relationship between them. For example, I am talking about the cities, Hyderabad, Delhi, Bombay, Calcutta. There is no relationship between the cities. There is no order or something unless I talk about population of each of the cities or area of each of the cities, then there might be an ordering. But city names as such may not have any kind of an ordering. In that case, I should not do label encoding or ordinal encoding. It is better to do a nominal encoding or otherwise called as dummy variable encoding. Or in some cases, it is also called as one hot, or this is the most one hot encoding. This is what is typically suggested. Okay, so we are so here we are doing a label encoding. I have discussed about the label encoding. You are seeing that every column has been fitted with either 0, 1, 2 kind of a such. Then similarly, right now, this has been overwritten. Okay, so all the columns are now showing the typical labels. So 0, 1, 2 kind of values. So if you are applying the label encoding on one of your columns, this is what you do. You import the label encoder, right? So you are initiating the label encoder. You are doing a fit transform on a particular column. Now, when you are doing that, obviously you will get, now you are actually overwriting on the top of it. So you could see that they have been fitted with 0, 1, 2, 3, 4 kind of numbers, right? So that is what you are getting. So now it is only having numerical values. So whatever was the string earlier, but now you use the label encoding to typically convert that string into a numerical value. So now you have, let's say you have only nominal variables. So variables wise, possibly by now you are clear that there are some nominal variables where ordering of the data is unimportant. In these kind of cases, I would not suggest label encoding. Better to go with one hot encoding, right? Like cities where there is no order. The order does not make any kind of an importance. On the other side, we have an ordinal data where order is important. Right? So in this case, you can very well apply for either a label encoding, or there is also something called ordinal encoding. Now here, don't try one-hot encoding in this case, because I'll talk about one-hot encoding now. Probably that would increase the dimensions of the data and make the data complex. One-hot encoding increases the dimension of the data and makes the data complex. So when there is a ordinal variable, you don't use the one-hot encoding. Rather, it would be better that you do a label encoding, or you can go with an ordinal encoding. So let's say you are having blue, green, red, yellow, where there is no order. Order does not matter. Whereas on the other side, if you say primary school, secondary school, graduate, postgraduate, there is an order. So if there is an order, it's always better to go with label encoding or ordinal encoding. Similarly, you are talking about salary brackets. You could see that there is an order, but at the same time, the gap is uniform between the groups. So there are three different kinds of data sets. The first one is called nominal. The second one will be called ordinal. And the third one is typically called an interval scale of data. The intervals are uniform across. That's the reason it is called interval scale of data. Okay, so we are clear on all the three. Now, wherever there is a nominal data primarily, it is always better not to use a label encoding. It is better to go with one-hot encoding. Now, what happens in a one-hot encoding, we'll talk about with a simple example. So the data, customer 1, customer 2, customer 3, customer, okay, we'll put some customers. Customer 4, customer 5, customer 6, customer 7. Okay, so I'll say the city, Hyderabad, Mumbai, Bengaluru, Mumbai, Kolkata, Hyderabad. Let's say if I have something like this, right? Now, obviously, these are nominal variables. This is a nominal variable. Now we'll have to go with what is called one-hot encoding. So in one-hot encoding, what happens is it will look out for all the categories that are present in this column. The categories are H, M, B, K. These are the 4 categories that are present. So so out of these 4, let's say if there are n categories, n minus 1 will be selected. Probably the first one, either the first one, which is like alphabetically B, or the last one, which is M. One of them can be dropped by default. Okay. Then the remain, let's assume that the first one is dropped. Now what will happen? The H is created as one new column name. Hyderabad is a new column name. Mumbai is another column name. Mumbai is created as another column name. Kolkata is created as another column name. Right? Now, because the C1 is having Hyderabad as a city, so this would be written as something like that. Under Hyderabad, there will be a 1. and under all the other cities, it will show as 0. Now, similarly for Mumbai, it is going to become something like this. Now, for Bengaluru, it is going to be 0, 0, 0 because none of the three are matching. For Mumbai, again, it is like this. Mumbai, it is like this. Kolkata, it is going to be like this. And again, Hyderabad, it is going to be like this. So basically what you could see is all four cities have been very well represented by a decent combinations of ones and zeros. So I can use, if there are n categories in the data, I can create n minus 1 new headings. Now you may ask, why not n new heading? Why n minus 1? Now what could happen is, if I create one more column called, right, if I create one more column called Bengaluru, and I put here 0, 0, 1, 0, 0, 0, 0. What could happen is, I can simply, if I say, I simply add up these four columns, right? If I do some linear operation on these four columns, it would become 1, 1, 1, 1, 1. So this will become a zero variance column. And as we already know, the zero variance columns would always be a problem for our data and they need to be removed. So no arithmetic. This is actually, it uses a lot of concepts of matrices and all. So this kind of matrix is typically a singular matrix. And we say that the inversion is not possible for a singular matrix. And which means solving the singular matrix will become a problem. So you will not get an appropriate solution. You would always get your error messages. Now that is the reason, to avoid the singularity, one of the columns is typically knocked out. When you say knocked out, it is taken as a part of the intercept behavior itself. For any model, the base model or the typical intercept behavior is what is understood as one of these columns, one of the omitted columns, and the all others are, that's the reason we say 0, 0, 0 is like one column, which is the typical, let's say the one that is starting with the most early, but you can very well change that ordering as well. So this kind of mechanism, after that I can remove the city column altogether and I'll only retain the HMK kind of column. Is that clear now, Dev? All right. So there is no answer to YB. I mean, not necessary. You can remove anything, right? You can remove anything, but the default thing is default thing. It's like the first one. The first is always in a kind of alphabetical order, right? So you will have a kind of a parameter which says drop first equal to true. Or if you say drop first equal to false, then it would drop the last one. Otherwise, you will have to write your own thing onto as to which one needs to be dropped. And it has no meaning also. I mean, it's just that it has created. See, basically what is happening in terms of numericals, Bengaluru will become a 0, 0, 0. Whereas Hyderabad may become 1, 0, 0, Mumbai may become 0, 1, 0, and Kolkata may become 0, 0, 1. So all of them are getting their adequate representation, right? So when you are building a model, when you are typically here doing a prediction for Bengaluru, you will put 000 for Mumbai and Hyderabad and Kolkata, and whatever is the prediction that comes, that is the prediction for Bengaluru. All right. Okay. So that is what is one-hot encoding, or sometimes called as dummy variable encoding. I think here I cannot apply it on the categorical data, because the categorical data has already got converted. Okay. So possibly what I'll do is, we'll just check for some other column. Here there is no point in me doing this on this one. Okay. So let me just check. I'll just what is that? DF, right? Okay, we have this, right? We'll have street or something which has okay, I'll take the roof style. Okay, we'll take the roof style and we'll convert. So basically, let us see first what are all the things that are available under the roof style. Before I convert it, I would also go ahead with okay. So let me first print what are all their value counts of this. So you see cable is 1140, hip is 282, flat is 13. So there are different kinds of roof styles. So what I would do, I want, because this is a complete, there is no order associated with it. So doing a kind of label encoding would not be a good idea here. So that is the reason I would typically, I have to go with one-hot encoding, sorry. So I will have to go with one-hot encoding, not the label encoding. Or we can very well go ahead with, we can very well go ahead with, there is a pd.getDummies. You can very well do this exercise also. So this is one more way of doing this. So you can very well go ahead with you can very well go ahead with this one. Now you could see these are this is the way the columns got created. This is the way the one hot encoding got created. Okay. Because we have set printing for a maximum rows and maximum columns, right? So Gable has become one column with a value 1, Gambrel 0, Hip 0, Mansard 0, Shed 0. So wherever here it looks like it's a 0, 0, 1, it's like a hip kind of thing. So like that you could see that you can very well get the dummy variables like that. So these are called dummy variables because they take a value of only 1 or 0. They don't take any other values. That is what is the kind of a definition of dummy variable. Then one last thing, especially even with a categorical variable, the other thing that we can also do is what is called as hashing. This is possibly again coming from the domain knowledge itself, right? When we are talking about hashing, we are not doing any, see, basically it says hashing is more about combining, right? Though the word may look very, to a large extent, you can think of combining, right? Probably saying, let's say you have a frequency, right? Here you may say Kolkata is having a frequency of only 1. Or in the earlier example which we have seen, right, the roof tiles, somewhere when we have printed the roof tiles, we have seen that some categories, there are hardly 1 or 2 occurrences, right? Possibly again, if I really want to look at D of roof style, dot value counts, you see here, Gable is 1140, Hip is 282, but all others are looking very, very low in frequency, right? So one way we have discussed right at the beginning itself, when we are doing a data cleaning kind of operation, these kind of things where the number of occurrences are very, very low, it would be better to drop them because having these values in the model may not give a better estimates at all. So flat, gambrel, mansard, shed. So what can very well happen when I'm using hashing kind of mechanism is I can combine all these 4 and say others, because frequency wise they have almost nothing. So we can say right now our model will not take care of, will only cater to gable and hip kind of roof style, but all other roof styles are typically treated as one category called others. So until I get sufficient data in all the other categories, right now I can still consider all of them as others. So that way also sometimes what can happen is the overall goodness of the model can increase. So hashing is that's the way you are trying to merge multiple categories into one single category. So because of that, my total number of categories will come down. And even after that, I can still do a one hot encoding. But before I do a one hot encoding, I can do a hashing. So because of that, basically you can actually create that hashing using the business logic, right? Sometimes you will typically say I can combine. Let's say you are having too many states, right? Or sometimes you get pin codes, or sometimes you get too many states in the data. There are 40 states for which the very few observations are there for each state. So you can very well do some kind of an aggregation saying the southern region. So you combine Telangana, Andhra Pradesh, Tamil Nadu, Karnataka, Kerala, all these states, and you say South India. Similarly, Western India, Central India. So basically, the 30, 35 states that you had in the original data, you are trying to combine all of them into 4 different regions or 5 different regions. So this is also a kind of business logic based hashing technique. Right, I'll talk about the hashing probably slightly later, how we do them, right? So basically we have to write some if else kind of statements. You are combining all of them, so some kind of if else kind of statements have to. Sometimes frequency based hashing, which I think just now I talked about, right? So 10 occurrences of this, 5 occurrences of this, something like that. You combine all of them into others. So that is what is also another way of doing the hash. You could see here also in terms of frequency, probably these two, they are very low in frequency. So if you want, you can very well combine these two and simply say only 3 categories altogether. So, but there should be some kind of support from the domain to combine your categories as well. So I'll discuss about this. I mean, when we are taking up a few more assignments, even this kind. So just keep it in mind that these are some of the activities that you can very well do on the data. So we have. So with this, I think this notebook is almost done. So we handled outliers. Of course, some of them are pending, which will bring it in our upcoming sessions. Right, scale. Then we did some feature extraction, scaling, feature engineering, and finally we ended it up with categorical variable encoding. So these are some of the data cleaning and pre-processing tasks. And I think you guys should be really comfortable executing all these tasks on any other new data set as well. The next session is going to be an important session, feature selection, which variables can be dropped and which variables can be retained. How do I really ensure that the variables that I am retaining, they are going to add value to my model? So that is what I'm going to discuss in the next session. But yeah, I think I don't want to take it now. If anyone is having any kind of queries, I think I'll spend some time. Otherwise, we'll try to wind up the session for today. So this sheet has already been shared with you, so you can very well practice on the same. And you can also, it should always be better that you pull out. I suggest if as you are very serious, some of you at least, you should take up 1 or 2 other data sets and do all these activities on one single data set, so that you can really get that comfort of almost executing a kind of an end-to-end project. Yeah, PPT I'm going to share. Is there any mechanism to evaluate the impact of the featured variables? Yeah. So in the feature selection, we are going to talk about many such kind of scoring mechanisms. Right? Which one? So right from a very basic mechanisms to very advanced algorithm driven kind of mechanisms also we have. Right? If I'm you are trying to refer to the importance of each of the variables. If I have understood your question correctly, Paras, with the importance of each of the variables or something like that. Right? So what? So if that is the question, then yes, I mean, rather than trying to understand the impact after the model is built, we are trying to understand the impact before the model itself is being built, because I can knock out some of the unimportant variables so that my processing time and effort are reduced. So all this pre-processing is about trying to ensure that we are reducing on our processing time altogether. What is the pipeline? Okay, when we build a model, I will come back to the pipeline, but pipeline is nothing but series of steps, right? Okay, initially I do a, so basically it has been supported by scikit-learn, right? You can apply the various functions of scikit-learn in a sequence. Initially, you do the scaling. Then you apply one hot encoding. Then to that same data, you apply let's say some linear regression model. To that same data, you apply a logistic regression model. So what is happening is you are building a sequence of steps. So whatever is the output that is coming out of the previous step, you are taking as that one as the input to the next step. So that is what we call as pipelines, right? So we are talking about the same. You start with some data, you do something on that data by applying one scikit-learn function. So there is some output that comes out. You take that data as an input and do the next function. Something else comes out. You take that as an input and do the third function. And finally, you build your model. So all this is typically a part of pipeline. So when we are building a model, I will definitely build some models using the pipeline. It's not a mandatory requirement that you need to use. Possibly your coding is reduced a little bit by doing the pipeline exercise. Yeah, it is like you are combining all the inputting and pre-processing and even the modeling into a one single step. One single step means it does all these steps, but again, it gives a kind of, for you, it is like you are doing it in one step. Internally, it processes it in all the steps. Okay. Thanks a lot, everyone, for attending this session. So we'll move on to the feature selection in the next class.